Hello, my name is Ari Rubenstein, and today I'll be talking about how we can use reinforcement learning to design missed-thrust resilient trajectories. This is part of an ongoing collaboration between the Astrodynamics and Space Research Lab at the University of Alabama and NASA's Jet Propulsion Laboratory. If you look at the background of this slide, you'll actually see on the right a spacecraft trajectory going from Mars and rendezvousing with Earth. Now on the left, you can see the neural network that's acting as the controller for this trajectory. It takes in the spacecraft's state and the relative position to Earth, and as the different neurons light up, you can see their different activation weights, and the outputs, which are the in-path control angle, and the thruster curve. So in this talk, I want to answer three main questions. First of all, what is the missed-thrust problem? How does reinforcement learning work? And can we use reinforcement learning to solve the missed-thrust problem? Electric propulsion is an enabling concept for many new deep space missions. Unfortunately, their limited thrusting capability means instead of having to thrust for minutes at a time, their thrusting arcs are now measured in weeks and months at a time. A spacecraft has a 60% likelihood of entering a safe mode event every 200 days. And during one of these safe mode events, the propulsion system gets deactivated while the spacecraft focuses on generating power and communicating with Earth. Now, if a spacecraft enters a safe mode while it's supposed to be having a thrusting arc, this is called a missed-thrust event. And even just a 10-day missed-thrust event can delay arrival by 200 days or even cause the complete loss of a mission. Now, for a 1.1-year trajectory, we can see the number of missed-thrust events and their probability of occurrence. Note that the probability of 1 or 2 missed-thrust events is greater than the probability of no missed-thrust events. Furthermore, the cumulative probability of 2 or more missed-thrust events is greater than 50%. So the question isn't just, will there be missed-thrust events, but how many missed-thrust events and what will we do when they happen? Current approaches to solving the missed-thrust problem are to add additional fuel and time margins that the spacecraft can consume after a missed-thrust event. Additionally, you can place forced coasting arcs, which can then act as sort of buffers that you can again consume after a missed-thrust event occurs. There are other techniques currently in their early stages of development, but most often only deal with a single missed-thrust event. But as we saw earlier, as the trajectory durations grow, the number of missed-thrust events grows to be greater than a single missed-thrust event. In this talk, I'll assume you have no familiarity with anything in AI, so I'm just going to introduce some very short two-letter acronyms. In this talk, I'm going to make no distinction between artificial intelligence and machine learning. And just some examples of machine learning that you're used to are Kalman filters and linear regressions. Fourier analyses, where you have a Fourier series, is another popular application of machine learning. One of the newer forms of machine learning are neural networks. And these are function approximators, just like linear regression and Fourier series, but they're inspired by the structure of our brains. Similarly to the Fourier series, you need to find the weights and biases of your neural network. And this is called training your neural network. And there are three main forms of training. Supervised learning, which is when you have an input data set and you have the corresponding outputs for all of those inputs. Unsupervised learning is when you just have the inputs and you're trying to tease out patterns from those inputs. And then reinforcement learning, which is the main part of this talk, we'll cover now. So reinforcement learning is based on, can we teach the computers to learn the same way we learn? So as a young child, we'll touch a hot stove top, feel the pain, and then we remember that we shouldn't touch hot things because it causes pain. The idea behind reinforcement learning is the exact same. Can we let the AI explore the environment and get rewards and be punished? And then we'll store those memories of past actions and the consequences of those actions, and then we'll learn from these experiences. Going one level deeper into how reinforcement learning works, it's a repeated set of 3 steps, the first of which is exploring the environment. In this case, we have our dynamics. Because the misthrust events are stochastic in nature, we have some stochastic perturbations, and we have our controller, which takes in the state and the time. Now, in this case, our controller is going to be a neural network with some parameters theta, which are just the weights and biases. As we're exploring the environment, we're going to be collecting actions and their consequences, and then we have to estimate the cost function that we get from the rewards as we collect them. Finally, once we have estimated the return, we then need to update our policy. And for that, we are going to update the weights and biases through gradient ascent. Now, most AI and most machine learning in general uses gradient descent, but reinforcement learning anomalously uses gradient ascent in the literature, and so I'm going to be sticking with that style for the rest of this talk. Now, just to bring everything together about reinforcement learning, it has a lot of pros, like the fact that we don't actually need a model to train a reinforcement learning agent. We just need some way of interacting with the environment. Additionally, it can theoretically solve any optimal control problem, so both deterministic and stochastic problems, as well as problems where the problem itself is not differentiable. Finally, once we've trained our reinforcement learning agent on the model, it is computationally cheap to evaluate. Unfortunately, reinforcement learning is generally harder to implement in practice, and it likes to get stuck at local minimas. It's also only as good as the reward function you give it, so if you misprioritize a certain aspect, reinforcement learning will quote-unquote cheat and just maximize for that easy reward. And finally, while it's computationally cheap to evaluate, it's very intensive to train. Now that we know what reinforcement learning is and what the misthrust problem is, let's apply this to an astrodynamics problem. In this case, we're going to have a Mars to Earth transfer with some arrival tolerance, so we can arrive with some v infinity. We're going to try to maximize the mass optimality, and we're going to deal with a very low fidelity problem where it's Mars and Earth are both in circular planar orbits, and our spacecraft is under two-body dynamics using polar coordinates. Our spacecraft, which you can see on the right, has two control variables: U, which is its thrust fraction, which is the fraction of total thrust, which in this case is 1.3 newtons, and then beta, which is the in-path control angle. Now, earlier we discussed how reinforcement learning is very computationally intensive. But solving the corresponding deterministic optimal control problem is relatively easy. And in fact, if we wanted to go for a 1.1 year time of flight trajectory from Mars to Earth, you can see the solution in the bottom right-hand corner, starting at Mars and arriving at Earth. This was solved using a direct collocation method. And once you have the trajectory, you could create a dataset of the states and their corresponding optimal actions. You can then use this dataset to train a neural network using supervised learning. And we go over the workflow for this specific problem in a journal paper published earlier this year in Acta Astronautica, so I highly recommend you look at that paper to see the full workflow for training this neural network. But now that we can use that initial neural network, which I'm going to call the baseline neural network, we can provide that as the initial guess for the reinforcement learning agent for the stochastic problem. And that allows us to train all of our models on high-end consumer hardware instead of supercomputing power, which you'll often see in reinforcement learning problems. Now that we have the problem, let's look at both the baseline success rate, which is the fraction of trajectories that can be reconverged after the final misthrust event, and the post-reinforcement learning success rate. We can see that at all arrival tolerances, the success rate increases For example, at the 2.5 Earth sphere of influence arrival tolerance, the success rate after reinforcement learning increases to 99.6. Additionally, if we tighten the arrival tolerance to 1 Earth sphere of influence, the success rate again increases from 87% to 96.2%. Finally, if we tighten it an order of magnitude to 0.1 Earth spheres of influence, we can see that the baseline neural network doesn't perform very well. In fact, the success rate is less than 1%. But after reinforcement learning is applied, it jumps up to 54% success rate. Now that we've looked at the quantitative changes that reinforcement learning makes, let's look at what changes it's making qualitatively to the trajectory. This red line up here indicates the in-plane control angle, while this green line here indicates the thrust fraction at any time. And as you can see, it has a roughly bang-on, bang-off structure. Now, this is actually two plots overlaid. On the top, that has both the baseline and the post-reinforcement learning trained agents. In fact, you can see the baseline peeking out right here, where you can see the blue slightly not being overlapped by the green. So the changes it's making are very minimal. So minimal that if we'd have to subtract the two trajectories from each other in order to see the differences. And by doing this, we can see that the angle fraction has no real difference between the two. But in the thrust fraction, we could see the down and then up structure in the difference. And what that indicates is it's pushing the initial bang-on phase later in the trajectory. While in the second bang-on phase, you can see that goes down and then down again, which indicates that it's shrinking the duration of the second bang-on phase. If we were to look at other metrics, we can see that the reinforcement learning trained neural network can deliver an extra almost 1.5 kilograms of mass, while the delayedness changes negligibly. In conclusion, we've shown that reinforcement learning can make trajectories more resilient to misthrust events, and that after a misthrust event occurs, the reinforcement learning agents can repair the trajectory. And this is shown at a wide variety of arrival tolerances. In the future, we want to improve these arrival tolerances and tighten them further, as well as increase the model fidelity to include things like the ephemeris positions of Mars and Earth. Now, if you have any questions, I invite you to join us at the Artificial Intelligence and its Application to Space Missions session, Wednesday, August 12th, 2020. I will be there answering questions at 10:20 a.m. Eastern Time. I look forward to hearing from you then.